So when you do a tensile test, you produce something like this, a stress-strain curve. You also produce these for 3-point and 4-point bending. So I'll just talk you through some of the basic principles here. What I've shown here is just the beginnings of a stress-strain curve. I haven't shown going up to failure yet because they'd end up with too many words all over the board. This region here is what's called the Hookean region of a sample. Not all materials show Hookean behaviour. Wood, unfortunately, is one of those. But we can approximate, particularly with tensile testing, to Hookean behaviour over a certain strain and applied force. So Hookean basically means that the stress is linearly related to the strain. And if we divide the stress by the strain over this linear portion, we'll get something called the Young's modulus, which is called Ym there. So stress divided by strain is Young's modulus. And stress is measured in units of pressure, Pascal or megapascal or gigapascal. And strain doesn't have any units because strain is the incremental increase in length divided by the original length of the sample. And this incremental increase is due to the applied stress. So no units, but sometimes we measure strain in terms of a percentage. When you're calculating Young's modulus, do not calculate strain as a percentage because then you'll be out by a factor of 100. So it is stress divided by strain, nothing else. So this is the elastic limit here. Beyond that point, the sample begins to show plastic behaviour. And if we release the stress at any point and then allow the sample to return to its original shape by taking away the strain, you find it doesn't follow the same path. This is actually called hysteresis. The problem with this, of course, is the sample has actually changed. It now has a permanent deformation. I talked about this elsewhere when I was talking about the rheology of wood. It's quite complicated and it depends on the time over which you apply the load. So if we do this fairly quickly, if we apply this fairly quickly, we're not going to see this behaviour until quite late on. But if we apply the load very slowly, we're going to see non-Hookean behaviour coming in almost immediately, depending on how quickly we apply the load. So this duration of load thing is really important. It's also affected by the relative humidity, or how wet the sample is, what the moisture content of the sample is. So the whole range of behaviour there that is affected by the moisture content of the sample, the temperature at which you're doing the test, the previous history of the sample. So as you can imagine, it gets complicated. I'll show the rest of this behaviour in the next part of the talk because I'm going to end up with a very complicated diagram covered in words and I won't be explaining something, I'll just be confusing you.